Okay, so here we have an example of an average speed problem that involves two different moving objects. So if you want, take a second and pause the video and read the question to yourself so you know what it is that we're doing. All right, so let's go ahead and move on with this. So in this situation, you have a car that left a certain starting point at 8 a.m. It is driving at a constant rate of 50 miles per hour. And then you have an airplane that leaves 2 hours later, moving at a faster rate of 130 miles per hour. So common sense tells you that the airplane is going to definitely catch the car. So the question is asking, when will that event occur? So when will the airplane catch it with the car? So I highly recommend that you set up, some sort of organization chart to help you extract information and plug it in the right spot. So here in my work, I have car on the left side, I have airplane on the right side, car being object 1, airplane being object 2. And I went ahead and start with the average speed function, which is simply distance over time. So you notice on the left side here, all the variables have a subscript 1 because I don't know if those are the same as object 2. So a good habit is just go ahead and call them variables with subscript 1. And then on the right side, the same function, which is subscript 2. Okay. But if you read the problem earlier, you notice that here certain information is given to you. The speed of the car is given to you, and the speed of the airplane is given to you. And the other thing that's that's not explicitly stated is that they have to have the same distance. They left the same starting point, and when the airplane catches up with the car, they have covered the same amount of distance. So in my work, I went ahead and substitute 50 miles per hour here for the car. And you notice in the numerator, instead of calling it D1, I went ahead and got rid of the subscript 1 because I know that they have to have the same distance. And when things are the same, you don't need subscript. T1, that would be different because the car left 2 hours earlier, so I will keep the subscript in T1. On the right side, I went ahead and plugged in 130 miles per hour because that was given to us for the airplane. Again, in the numerator, instead of D2, I just call it D because that is the common term in this particular problem. T2 is going to be smaller than T1 because the airplane is moving faster, so it would take less time to travel the same distance. So here we have two functions with a common variable, which is D. I will go ahead and solve for D in both of these statements and then set them equal to each other. So to solve for D on the left side, simply multiply both sides by T1, so we have 50 T1. You notice I left out the unit miles per hour just to keep the work clean. And on the right side, we can do the same. We can solve for D by simply multiplying both sides by T2. So we have 130 T2 equals to D. And then you would want to set these two functions equal to each other because we don't know what that distance is, but we know that that is the distance that both objects have to travel. And that is the commonality between these two objects. Okay. So if you do that, you have 50 T1, which is equal to 130 T2. So you notice here you have one statement with two unknowns. So you have to get rid of one of these time variable, either T1 or T2. So at this particular step, it is entirely up to you to choose a perspective, whether you choose the perspective of the car or the airplane. But here I will go ahead and choose the car because I know that the car was the first object to leave and it left the starting position at 8 a.m. So in the wording, as highlighted there in yellow, it states that the airplane left 2 hours later after the car. So in my work, I will get rid of T2 because I don't know what T2 is. I just know that it left 2 hours after the car, which is denoted as T1. So instead of T2, I went ahead and substitute T2 for T1 minus 2. Again, the minus 2 is because it left 2 hours later. So it's in motion for less time. So by doing that, I now just have one variable, which is just T1. So if you do your math properly, distribute the 130 to T1, distribute the 130 to the negative 2, you should have this next statement, which is 50 T1 equals to 130 T1 minus 260. And then from here, we notice there's just, again, one variable, which is T1, combine like terms, and then just solve. So the combine like terms, I will go ahead in my work, move the 130 T1 to the left side of the equal sign, which will make it a negative 130 T1. So 50 minus 130 T1 will give you negative 80 T1. And on the right side, what remains after I've moved the 130 T1 is negative 260, which is carried down there in the next step. So from here, to solve for T1, simply divide both sides by negative 80, and you should get 3.25 hours. Okay, I do want to point out that it's important that you learn to interpret decimal place in terms of time. This is 3.25 hours. 0.25 hours is equivalent to 15 minutes, because for every hour there are 60 minutes, and then a fourth of 60 is 15 minutes. Okay, so you need to interpret this 3.25 hours correctly. If the car left the starting location at 8 a.m. and has been in motion for 3.25 hours, 8 plus 3 would make that 11 a.m. and then 0.25 hours is equivalent to 15 minutes. So the airplane in this statement will catch the car at 11:15 a.m. Okay, I hope that helps in terms of attacking these type of catch-up problems or leading problems. All right, good luck.